So today's video is about Dirichlet's unit theorem for function fields. So to begin, let's talk a little bit about Dirichlet's unit for number fields. So let's review the classical setting. If anything, just to draw an analogy to the function field setting. So let E be the units of a number field K. And let sigma 1 through R1, sigma 1 through sigma R1, these be the real embeddings of K into an algebraic closure of Q. And let's let sigma R1 plus 1 through sigma R1 plus R2 be the complex embeddings, pairs of complex embeddings of K into an algebraic closure of Q. The idea is we want to know something about the units of E as a Z module. And the idea is that we're going to try to embed the units E into kind of Euclidean n space. That way, well, I guess the idea is that we're going to try to show that the image then, if we embed E into kind of logarithmically into Euclidean n space, if we could show that the image is a lattice, then this will tell us about the structure of E as a Z module. It'll actually tell us that there'll have to be some torsion part, those will just be the roots of unity that exist in E, and then direct sum a finite number of copies of Z, right? So that's what lattices in Euclidean n space have to look like. So what we're going to do is going to take, let's let L be the map that takes E the units and maps it into R to the R1 plus R2 space, the trace zero subspace actually of this guy. Let's call that R naught. And the way that we're going to embed this in here is by taking epsilon and mapping it to delta I times the natural log of the absolute value of epsilon to the sigma. Okay, and delta I is going to be either 1 or 2, depending upon whether or not this was a real or complex embedding. So you might wonder, why is this embedding into the trace zero space? Well, it's because these are units, and so there's this natural, this kind of trivial relation among them, where if you norm them, or in this case, since we've kind of taken the log, to trace them down, they should trace to 0, because the norm on the units should go to plus or minus 1. Right? Okay, so that's, and then basically by taking this embedding into this Euclidean n space, it's not too hard to show that this is discrete. That's actually, for the image of the units in this space is discrete. That's actually not too hard to show. The hard bit is actually getting the rank correct, showing that it actually has that it's actually a full lattice in here. But there's lots of ways to do that. One way to do it is actually to show that there is a Minkowski unit. So for example, you could try to show something like that there is a unit like, let's think here. Well, there's lots of ways to do it, but anyway. But yeah, you can consult your algebraic number theory text, and you'll find a proof of that fact in there. But yeah, you show that it's discrete, and then you have to show that it's a full rank. That takes that's actually the most of the work. Basically the theorem comes out that the image of L is a lattice in this space. And so in other words, another way of looking at it is that the image of E via L is discrete and co-compact in R naught. Right? So then I guess this means that it's a full rank. It's a full rank lattice in here. And so that means, and since we're in the trace zero subspace, that means that the rank of E as a Z module is R1 plus R2 minus 1. We lost a dimension because of this kind of naive relationship amongst the units. By virtue of the fact that they're units, they norm to 1, and so they have to trace to and so when you map them logarithmically over to the Euclidean space, they have to trace to 0. Okay. But now let's so how does this generalize to function fields? What is the function field analog of all this? Let's talk about that next. Okay, so let's go over to the function field side now. So first let's fix some notation. Let little k be the rational function field with coefficients coming from a finite field fq. You're going to think about this as a valued field with the kind of infinity adic valuation. 1 over t, that's going to have value 1 over q. We're going to let a be the integers of little k. These are just polynomials with coefficients coming from fq. And C of A, and actually C of anything, we're going to be thinking of that as being, we're going to be thinking about it as an A module with the Carlitz action that we've been talking about, right? So C of A is really just A itself, but we're thinking of A as now as being being an A module with the Carlitz action. And we're going to use this notation kind of, C of, I could replace big A with, say, the integers of some extension of A, something like that. So COK, say something like that. That's going to mean OK, but with the A module structure coming from the Carlitz action. Okay, so K infinity, we're going to let that be the completion of little k with respect to our infinity adic valuation. So that's going to wind up being just a Laurent series with coefficients coming from FQ. We're going to let G be the Galois group of the separable closure of K infinity over K infinity. Let big K over K, that'll denote a finite separable extension. And big K infinity, this is going to be the product of fields over the complete. Each component is going to be K sub V, or K sub V is the completion of K with respect to one of the valuations that extends the infinity valuation. So what we're after now is some canonically. I guess we want to know what's the right analog for the units of C of A, or C of any integer ring. What is the right analog of unit in that context? In other words, I suppose we want to know, looking at A as a Carlitz, or sorry, looking at A as a module with a Carlitz action, is there some canonically defined, finitely generated module of units, kind of like there is in the classical setting, right? So yeah, in the classical setting, the number field setting, you have your ring of integers, and then the units of the ring of integers. This is going to kind of decompose into a finite number of copies of Z, and then perhaps with some torsion part. So we want to know, what is the right thing to look at here? Is there something, looking at the integers as a Carlitz module, is there kind of an analogous thing? And you might wonder, well, what if you just look at the classical units of A? As it turns out, these aren't even closed under the Carlitz action. Thinking of the classical units of A as an A module with the Carlitz action, it's not even an A module by virtue of the fact that it's not even closed, and that's easy to see. So we're going to need something different, and that's kind of what all this is about. So what do we expect out of this unit module? What would we like to be true in analog with the classical setting? I suppose we would like, whatever we're going to call the unit module, we'd like it to kind of decompose into a finite number of copies of A, right? And in particular, we kind of have a sense of how many copies there should be. Like in the classical setting and in the number field setting, the units decompose into R1 plus R2 minus 1 copies. We're going to see here that the unit module that we're going to construct decomposes in kind of a similar way. The rank as an A module is going to be very similar. Let's see how that's constructed. So let's begin with this exact sequence that we get from Carlitz. So we know that there is a discrete, a discrete submodule of K infinity. That's the kernel of X sub C. I think Rudy talked about that last week. We actually know what this is explicitly. It winds up being a number of copies of multiples of pi twiggle. And actually, the number of copies is precisely as many extensions of the valuation v to k that actually contain pi twiggle. So for exactly as many kv as there are that contain pi twiggle, that's how many copies there are of that guy showing up here. This is kind of analogous, if you want to look for a number field analog of this exact sequence. One thing that you could, the thing that's kind of playing the role of lambda k is something like 2 pi I to the R2. This is kind of representing something it's representing like the period of the exponential map, and the number of copies is corresponding to the number of places that actually contain that period. In the same way that, if this is 2 pi I to the R2, it's like the number of complex places. It's like the number of complex, places of that extend V. That extend our valuation V to K. Right? Okay. So anyways, we have this exact sequence. We know that the exponential, that the exponential map fits into this exact sequence that goes back to Carlitz, right? So given this short exact sequence, we could take G invariants of this exact sequence, and so we can derive some cohomology, right? So yeah, by lambda k to the g, I just mean the g invariance of lambda k. Where again, g is our Galois group of k infinity sep over k infinity. The g invariance of k infinity sep, those are obviously just going to be k infinity. That's just just typical Galois theory stuff. In the same fashion here, ck infinity. The g invariance of ck infinity sep, that's going to be ck infinity for the exact same reasons. And then we have this kind of connecting map into the first cohomology group of lambda k, right? And we know that the next guy is going to be a 0, because the next guy, I guess, would be h1g k infinity sep, and that's going to be 0 by Hilbert's theorem 90, essentially, the additive version of Hilbert's theorem 90. So, so we get this exact sequence. And let's let O sub k be the integers of big K. Then the fact that COK is a subset of CK infinity, this is going to induce a map which we're also going to call kind of delta from COK into H1G lambda K. That's just going to be the restriction of this connecting map up top. So it's the kernel and co-kernel of this map that we're going to want to take a look at. And yeah, it's going to be a benefit to realize that H1G lambda K is going to be isomorphic to CK infinity mod x, or the image under the Carlitz exponential of K infinity. And that follows easily, that's just from this line here, right? So yeah, so looking at the kernel and co-kernel of this map, the kernel of this map is what we're going to wind up calling the unit module, and the co-kernel of this map is what we're going to wind up calling the class module. And how exactly these are good analogs of the units and the kind of classical units and the ideal class group and the number field setting. Yeah, the exact reason why these are good analogs for those we'll discuss in just a moment. It was left kind of unsaid, but just to be explicit, this exact sequence, this is an exact sequence of A modules, and it's also an exact sequence of G modules as well. So we can think about these as being A adjoint G modules, right? The G action on K infinity is just going to be kind of coordinate-wise. We know K infinity decomposes into a product of completed fields, right? So the Galois action is just on the coordinates. And CK infinity, the Galois action on that is exactly the same. It's just now, remember that K infinity and CK infinity are really the exact same sets. We're just kind of thinking about them as being, we're thinking of this as being kind of an A algebra. Well, the action of A on K infinity is just kind of a normal left multiplication. The action of A on CK infinity is the Carlitz action, right? So, so it makes sense to take G, and it's easy to show that this is a G equivariant exact sequence, and so it makes sense to take G invariance. So just wanted to make that explicit. Okay, so we have our connecting map delta from COK into H1G lambda K. And again, remind you that this is isomorphic to CK infinity mod XC of K infinity. So we're going to let the kernel of delta, we want to call that our unit module, we'll denote it by UOK. The co-kernel of this map, that will be the class module, denoted by HOK. And so just kind of a quick thing to kind of look at. So first, notice that UOK is actually contained in COK. This is just by virtue of the fact that it's the kernel of a map from COK. And let's call our blackboard U, let's call that the inverse image of COK intersect K infinity. So when you're looking at this, the relationship between our blackboard U and our unit module is that this guy is the exponential of this guy, right? And when you're looking at this guy, you notice that it really kind of looks like a lattice of logarithms, right? So, and yeah, we know that the exponential of this guy is going to map into the kernel here, just by virtue of the fact that, why is the exponential of this going to wind up being in the kernel of this map? Well, it's precisely because of this identification here, right? We know that anything that's going to be in the exponential and that's going to be an XC K infinity, that's going to wind up being 0 when you push it across here via delta, right? So obviously this will get mapped into the kernel of this connecting map, right? And when you're looking at this, yeah, it does look a lot like, you're taking logarithms of all the integral points, right? So this looks a lot like a lattice of logarithms. And that's an important thing to kind of notice. I mean, that's actually kind of the thing that makes a lot of this work. And it's something to take as kind of why this should be an analogy of the unit module, right? Classically in a number field setting, it was kind of the other way. We started with units and then we took their logarithms to start saying things about them, right? Here, what we're kind of doing is we're actually kind of starting with what we want to call the unit module. Well, I guess it's kind of the same thing. I mean, you have your unit module here, and then in order to say things about this unit module, you kind of take the logarithm of this set. So that identification is going to wind up being very valuable. In the same way that in the classical setting, in the number field setting, it was very valuable to take units and take their logs. I guess the philosophy being the units are kind of mysterious, at least at the forefront, but when you take their logarithms, you've now kind of embedded them into some Euclidean space, and you could use all the facts that you know about linear algebra and various things there, to say various things about the units, right? So the fact that in the classical setting, like when we map over the units into Euclidean space, the fact that we know that it creates a discrete lattice of full rank, this is actually what then determines what the units are, what the structure of the units are as a Z module. Same thing is going to kind of help us out here. We're going to be able to exploit the fact that we kind of thinking about, exploit the fact that this is a lattice with logarithms and its exponential is what we're calling the unit module. We're going to exploit that fact to say there are various things about the A module structure of this guy, where the A action is actually the Carlitz action. So picking up where we left off before, we have this exact sequence. We have bold blackboard U, our kind of lattice of logarithms. It maps onto what we're calling the unit module via the exponential, and its kernel is lambda k. Right? Okay, so what are some facts? Again, we kind of want to know how is this an analogy with how is the unit module or the right analogy of units, right? So some facts that we have Lenny Taelman to thank from his paper on Dirichlet unit theorem for Dirichlet modules. Something we could say is, well, for example, our unit module UK, it's a finitely generated A module, just by virtue of the fact that it's an A module is better than what we had before. But it's a finitely generated A module with what appears to be kind of the right rank. And the rank is precisely the index, or the degree of big K over little k minus the A rank of lambda k. And remember that lambda k is kind of like, it's playing the role of like R2 copies of 2 pi I z, right? So if you compare this to the classical setting, what is the rank of the units in the classical setting? Well, it should be the degree of our extension, R1 plus 2R2, where again, R1 and R2 are playing their usual roles. R1 is the number of real embeddings, and R2 is the number of pairs of complex embeddings, right? So in the classical setting, the rank of the units as a Z module should be R1 plus R2 minus 1, which is basically what this is. It's R1 plus R2, or 2R2, that's the degree of our extension, minus essentially R2. We do have to add an extra dimension in the number field setting to account for the fact that our units actually, there's this trivial relation where they all norm to plus or minus 1. So that seems to be absent here, but still. Yeah, time will tell, right? But anyway, this does seem to be kind of the right flavor for sure, right? So UOK is a finitely generated A module with what appears to be the appropriate rank. U are a kind of lattice of logarithms of our unit module. This sits inside K infinity, and it's discrete and co-compact in the exact same way that in the classical setting, our lattice of logarithms of units is co-compact in Euclidean R1 plus R2 minus 1 space. Right, and and by virtue of the fact that that we know that this is discrete and co-compact, this gives rise to a notion of kind of co-volume of U and K infinity, which is kind of what I'm talking about. I guess is it gives rise to a notion of regulator in this setting, right? So we can kind of measure the size of the units in some sense with this regulator. Another reason why perhaps you would want to call this you'd be tempted to call this a unit module is because it contains all the Carlitz torsion. So in other words, It contains all of those elements x of COK such that Cm of x is equal to 0 for some m and OK. In other words, this is like saying that it contains all the roots of unity. So yeah, so it contains the roots of unity. It also contains Anderson's construction of cyclotomic units. That'll be the topic perhaps of another video. But yeah, there is an analog of cyclotomic unit in this setting, and it was constructed by Anderson, I think, in his paper, 1996 paper. And yeah, we'll talk more about that specifically later. But anyway, yeah. So the point though is that our unit module seems to kind of contain all the right stuff. It contains kind of the torsion bits. It contains the cyclotomic units. Has the right rank as an A module. It's the divisible closure of the cyclotomic units. So it seems to be just the right guy to look at. Kind of going on the other side of it, HOK, what we call a class module. Lenny Taelman has shown that this is finite. It's a finite A module. A finite A module with a Carlitz action. Of course, same thing goes on here. I'm thinking of UOK as an A module with a Carlitz action. Yeah, and so necessarily then, by virtue of the fact that A is a PID, and this is some finite module over A, HOK is going to have to decompose into a certain number of copies of quotients of A, right? And therefore, it has kind of a character. You can kind of think about it as having kind of some sort of characteristic, or really what I'm really just talking about is something analogous to the class number or the order of the class group. And as it turns out, we haven't really mentioned much about why we're calling this the class module. How is this the right analog of the class group in the number field setting? The only thing that maybe we'll say about it now, we'll save the majority of that for the next video. But what we can say about it now is that, well, there's very large and deep kind of categorical reasons to be calling these things the unit modules, or to be calling UOK the unit module and to be calling HOK the class module. So yeah, so the reasons that kind of go beyond the scope of this video for why these analogies are being drawn, but it is reassuring that what we're calling the unit module kind of has has these qualities: the fact that it's finitely generated of correct rank, its lattice of logarithms is a discrete and co-compact, it contains all the right kind of torsion units and so forth. And there are also kind of reassuring reasons to call HOK the class module. In the same kind of way, and one of which that we're going to see, I think in the next video, is that the order, this class number, is related to, well, yeah, I guess the class number, the regulator of our units, and kind of special, special characteristic p-valued L functions and zeta functions. These are all kind of related to one another, like we should expect if we're going to be calling this the class module and this guy the unit module. So, for example, and this draws an analogy between this stuff and the number field setting. For example, it's known that there's a relationship between the classical regulator of the units, the class number, and certain values of, the residue of the zeta of the classical zeta functions at 1. So in the same way, we're going to be able to see an analogy between, this class number, this analog of class number, the regulator of our units, and characteristic p-valued L functions and zeta functions, the special values of those.